Two identical spaceships are connected by a delicate string. They start accelerating very close to the speed of light at exactly the same time and at exactly the same rate. The question is, as they accelerate, will the string stay intact or will it eventually snap? This puzzle is so counterintuitive that in the 80s, even the top physicists couldn't agree on what the right answer was. And in fact, even the person who got it right, turns out that he got it right for the wrong reasons. And that's why even today, some of the most popular videos on YouTube on this topic still miss what's actually going on. But I think I've finally cracked it. And the reason I'm sharing this video is not just because the real solution is truly elegant, but because of its far-reaching consequences. It led me to eventually think about black holes in a way that I had never before, the way physicists actually do. And it eventually pushed me into rediscovering Penrose diagrams from scratch. But I'm getting ahead of myself. Let's go back to the puzzle. If both ships accelerate together at the same rate, their separation should stay the same, right? And if the separation between them stays the same, the string is never pulled. So it should just stay intact. So why on earth would it ever snap? Well, remember when you go close to speed of light, Einstein's relativity starts kicking in. One famous prediction of relativity is that moving objects are shorter in the direction of motion compared to when they are at rest. This is called length contraction. Now, since everyday speeds are much slower than that of light, whose speed we usually choose to be 1 in relativity, we just don't notice this effect at all. But of course, close to speed of light, it's huge. For example, if the ship was traveling at say 87% the speed of light, then its moving length would be half when it's at rest. This means as the ships and the string speed up, they tend to shrink. So the big question is, what does that do to the string? How does length contraction affect the outcome of the puzzle? In the 80s, the physicist John Bell, yes, the same John Bell of the Bell's theorem who disproved Einstein's hidden variable assumptions of quantum mechanics, he argued that the string must snap. He says, look Mahesh, since the ships start accelerating at the same time, the distance between the ships should always stay the same. But of course, the ships and the string contract. However, since the string is tied at the ends, it can't freely contract. So stress starts building up. And as a result, it eventually snaps. But many of his colleagues at CERN disagreed. He says, and I quote, "A distinguished experimental physicist refused to accept that the thread would break and regarded my assertion that indeed it would as a personal misinterpretation of special relativity." But what was their argument against it? Well, they argued that if the whole system is accelerating together, why wouldn't the whole system contract together? Then look, there will be no stress in the string and so it wouldn't snap. And remember, motion is relative. So from the ship's perspective, they're always at rest relative to each other. So there is no length contraction between them at all. It's the rest of the universe that's moving backwards and contracting. So again, no stress on that string and it stays intact, which means this reasoning seems consistent in all frames. And so for me, this reasoning sounds super intuitive. And I'm guessing the same is true for most of you. About 60% of you answered that the string wouldn't snap in the community poll. But what's the consensus? Well, again, Bell says, we decided to appeal to the CERN theory division for arbitration and made a not very systematic canvas of opinion in it. There emerged a clear consensus that the thread would not break. So that's it. End of story. This is the correct answer and Bell is wrong, right? Well, Bell was actually pretty convinced that he was right. And so he popularized this puzzle by writing a chapter in his book called How to Teach Special Relativity. In there, he explained in excruciating detail, down to the level of atoms and electromagnetic fields, why the string should snap. And today, the consensus is that Bell was right. the string indeed snaps. That's why we call this today as the Bell's spaceship paradox. But why? Why does length contraction work this way and not this way? And what does it look like from the perspective of the people inside the ship? And most importantly, how can we figure this all out ourselves? Well, at first I thought I should look at Bell's original argument, but like I said, it's way too technical. It defeats the purpose of gaining some intuition. A breakthrough came for me when I went through the book Relativity Visualized by Louis Epstein. Oh my God, that totally blew my mind. So Epstein, why does length contraction work this way and not this way? And Epstein says, Mahesh, what exactly is length contraction according to you? Well, moving things are shorter compared to when they're at rest. And Epstein says, no, they're not. That's a misconception. I'm like, what? Look at this pen. This is how long it looks right now. But what if I rotate it? It looks shorter. Not because it actually got shorter. The pen did not get shorter. It just looks shorter because now you're looking at it from an angle. So when you're looking at this pen directly, the length that you measure is exactly the same as its true length. But watch what happens as the pen rotates. The measured length gets shorter. Not because the pen actually got shorter. It didn't. Its true length is still the same. But because you're now measuring it from an angle. It's all about geometry. So the key lesson over here is that we were never measuring the pencil's length in the first place. All we are measuring is its projection onto our axis. That's why this is also called the coordinate length. And the pencil's true length, we also call it the proper length. So look, the proper length didn't change. The pencil did not get shorter. It just rotated, and that's why the measured length got shorter. This is length contraction. This sounds incredibly amazing, but Epstein, there's a problem. Our space shuttle is not rotating, it's accelerating, right? So how do you explain what's going on over here? And Epstein says, but Mahesh, acceleration is rotation, not in space, but in space-time. When a spaceship is at rest in space, it's still moving through its own time, its proper time. And this speed with which it moves through space-time is the speed of light. In fact, everything in this universe, including you, me, donkeys, we all move through space-time at only one speed, the speed of light. It's just that when we are at rest, all of that speed is directed through time. That's why the spatial velocity is 0 and our time ticks at full speed. But what happens when this space shuttle accelerates? Well, as it accelerates, the speed through space-time cannot change. It should still be the same, but the direction does. The velocity vector tilts, and as a result, its spatial velocity increases. So look, acceleration is rotation in space-time. And that's why when the spaceship is at rest, you measure its length head on. So the measured length equals its proper length. But when it's moving, look, the length you measure becomes shorter than the proper length. Not because the ship physically shrank, not because it got shorter, but because it rotated. This is length contraction. So the faster it moves, the more it rotates and more the length contracts. This is insane. So length contraction is not that moving things are getting shorter. No. Instead, it's just that moving things are rotated in space-time, and so we're just measuring it from an angle. It's an artifact of measuring something from an angle. That's amazing. But wait, I am not fully sold yet. Epstein, does the math work out over here? Turns out, it actually works out beautifully. See, all we need to do is now find a connection between its true length and the measured length, right? How do we do that? Well, just complete the triangles. And look, these two triangles are now similar. So we can say the measured length divided by the true length should equal this side divided by this side. Now we usually take the speed of light to be 1 in relativity, so let's call that 1. Then what exactly is this side? Well, from Pythagoras, we can say that is the square root of 1 minus v squared. And so that's where that root of 1 minus v squared comes in, the length contraction formula. Isn't it amazing? We just derived it in a few steps, and isn't this so elegant? The math works out. Wow. But wait, I'm still not convinced yet. I have one last critique, okay? When the pencil rotates, look, in the horizontal, its length contracts, but the vertical length increases, right? So shouldn't the same thing happen to our space shuttle? As it rotates, the spatial length contracted, but shouldn't the temporal length increase? What does this temporal length signify? Epstein says, well, in the ship's frame, two perfectly synced clocks stay in sync even as the ship accelerates. So the temporal distance between the clocks in the ship's frame is 0. But in our frame, they go out of sync. The clock at the back will be ahead in proper time compared to the clock at the front. The temporal length equals how much the clocks are out of sync. So look, as the ship accelerates, the spatial length decreases, but the clocks go more and more out of sync, so indeed the temporal length increases. Another way to think about this is that in the ship's frame, 1 second in the front is simultaneous with 1 second at the back. But in our frame, 1 second in the front of the ship is simultaneous with 2 seconds in the back. So this shows that simultaneity is relative. That's amazing. We know that is to be true, but now we can see it in another way. That's amazing. But now this brings up the biggest problem with Bell's original explanation. Bell says as the string and the ships accelerate, they try to contract. However, the string's ends are tied, therefore it can't contract, and that produces the stress, and that snaps the string. But we just saw length contraction is just an artifact of measuring something from an angle. It's just geometry. So it cannot cause stress. And that's what makes this puzzle so puzzling. Bell's original explanation is wrong. I mean, just to be clear that we are on the same page, the string does snap. There is stress. That part is true. But saying that length contraction causes the string to snap, that is wrong in my opinion, because length contraction is just geometry, nothing more. And that's why I think even the most popular explanations on YouTube today about this topic is misleading, because they too, like Bell, attribute that stress to length contraction in our frame. So if length contraction is not the cause for this stress, what is actually generating it? What truly makes the string snap? And Epstein says the answer has been in front of us all along. It's acceleration. But how? I mean, both the ships are accelerating at exactly the same rate. How does that produce stress in the string? It's kind of like how trying to accelerate your learning can sometimes produce stress, unless you're using Brilliant, the sponsor of this video. What I love about Brilliant is that, just like in my videos, it focuses on intuition and hands-on approach to rediscover ideas yourself, and it lets you get started for free. They have a ton of courses in math, science, programming, and look, even AI for that matter. And my favorite part is that you're not just watching a passive video. No. You are instead being challenged and forced to reason, which is when learning truly happens. I think that's why I've been using and recommending Brilliant from way before they ever started sponsoring me. For example, take their course on thinking in Python. You directly start by working on a security-related project. How awesome is that? It teaches you about variables and dependencies and Boolean logic. And soon you start writing codes to hand various login conditions. And pretty soon you'll be working with advanced loops like big O notations and whatnot. What's more important is that the viewers of FloatHeadPhysics can get started for free. That's right. Just go to brilliant.org/FloatHeadPhysics and you can try everything Brilliant has to offer for free for a full 30 days. The link is also in the description, and if you want, you can scan the QR code as well. And if you do like it and you want to make a purchase, then you'll also get a 20% off on the premium subscription. Okay, so happy learning. Now let's get back to the video. So again, if both the ends of the string are accelerating at exactly the same rate, how exactly does that produce stress in the string? And Epson says, Mahesh, for a moment, forget about both the shuttles. Just consider a single space shuttle accelerating very close to the speed of light. His question is, if we were to keep a couple of accelerometers, remember an accelerometer measures acceleration using a physical effect, like a spring compressing. The greater the acceleration, the more the spring compresses. So if you place one at the back and one at the front, will they read the same value or different values? Well, my instinct says, since the whole ship is accelerating together, they should read the same value. Both of the accelerations must be exactly the same. The whole ship should have the same acceleration value. But if we remember that acceleration is rotation in four-dimensional space-time, and remember that when something rotates, like a door, the outer edge moves faster than the inner one, right? So the same thing must happen here. The behind should be moving faster than the front. So the back of the ship should at any given moment have a higher speed compared to the front of the ship, which means the back of the ship should gain velocity quicker than the front, which means the back of the ship should have a higher acceleration compared to the front. Oh, wait, that doesn't sound right. So let's think a little bit about this. At any given moment, the back of the ship is having more speed compared to the front of the ship. And that explains why the measured length contracts. So that makes sense. Okay. But I'm thinking, if the back of the ship is literally moving faster than the front, shouldn't the ship literally shrink? Like, shouldn't it physically shrink? Why doesn't that happen? Well, that's because, remember, what's simultaneous for us is not simultaneous for them. Now, for us, at any given moment, the back of the ship is moving faster than the front. But if I consider a particular moment in their frame, look, the back and the front have the same velocity. Again, if I consider a particular moment in their frame, the back has the same velocity as the front. Oh my God, this is so wild. So for a ship to maintain its rigidity as it accelerates, the back should indeed have a higher acceleration compared to the front. This is so counterintuitive. Of course, it makes sense if you think about acceleration as rotations, but still, man. Okay, so the now obvious question could be, what if the back and the front had exactly the same acceleration? What would happen now? Well, now, at any given moment in our frame, the front and the back would have the same speed. That means the measured length would remain the same. It wouldn't contract. But how can that be? How can the measured length stay the same while the shuttle is rotating in space-time? It cannot unless the shuttle physically stretches as it rotates. Oh my God. Now we see the full picture. If the front of the ship has a smaller acceleration compared to the back, we might expect the ship to physically shrink, but it doesn't. Its proper length stays the same. Of course, the measured length gets shorter, but that's just an artifact of the whole thing rotating. So there will be no stresses. There will be no shrinking. None of that is happening. In contrast, if the front and the back of the ship had the same acceleration, then we might expect the proper length of the ship to stay put, but it doesn't. In fact, the proper length increases and there will now be stresses generated inside. Of course, the measured length stays the same because as the ship is rotating, it's also stretching. Oh my God. This is what's going on. So this is the true key to the puzzle. So moment of truth, folks. Now that we understand exactly how acceleration works in space-time, can you pause the video and solve the Bell's spaceship paradox once and for all? Pause and bring it home. Give it a try. All right, here we go. Since both the ships start accelerating at exactly the same rate and exactly the same time, the ends of the string have the same acceleration. Therefore, the proper length of the string and the proper distance between the ships increase. This is what's truly happening. And remember, this statement that we have made is an absolute fact. We're not talking about measured lengths, which are dependent on reference frames anymore. We are talking about proper length and proper distances, which is an objective fact that everybody agrees on. So this is truly what's going on. And so as the string is being pulled, that produces the stress. But whoa, wait a second. One last question we could be having is, shouldn't the same thing happen to the space shuttle itself? Even for the space shuttle, the accelerations are the same to begin with, probably. And so shouldn't there also be stresses generated inside? Yes, it happens, but we are assuming that the material that makes up the space shuttle is pretty strong and it can handle that stress. And so look, as the stress pulls on the ends, the acceleration of the front will decrease slightly and the acceleration of the back will increase slightly. Eventually, the ship settles into the correct acceleration gradient needed. And when that happens, the stress stops further increasing. And from now onwards, the ship maintains its proper length and continues accelerating rigidly. But of course, we're assuming the string to be quite delicate because it's a string. So it won't be able to handle that stress, and that's why it snaps. But of course, what would we measure in our frame? Well, as the ships and the string accelerate, the proper length and the proper distance is increasing. Remember, that's an objective fact. But because it's also rotating as it stretches, look, the measured length stays the same. And that's why this stress generated seems mysterious, because we don't measure a change in the length, but its proper length is increasing. So the mystery disappears once we realize that the proper length and the proper distance between the ship has been increasing all this while. And so the string is literally being stretched, and that's why eventually the whole thing snaps. Paradox resolved. But now let's take this to the next level. Ready? Suppose we have a bunch of ships at rest, and we want them to start accelerating at the same time in such a way that the proper distance between them stays a constant. In other words, each ship should always see the others at rest relative to itself. How should they all accelerate? Again, our instincts might suggest that they should all have the same acceleration, but now we know that's wrong. The ships in the front must have a smaller acceleration than the ships behind. But wait, if all of them are at rest relative to each other, could they tell whether they are accelerating in empty, flat space-time or hovering near a black hole? No, because near a black hole, the situation is quite similar. The ship closer to the horizon must fire its engines harder than the ones farther away. So these two situations are pretty much identical. That means we can use accelerated observers in flat space-time to model black holes. And when you do that, a beautiful space-time diagram emerges, one that lets us predict the true physics of black holes. And when you zoom out far enough, you discover the Penrose diagram. All of that in the next video, so stay tuned.